Okay, so welcome back. Now that we've all had coffee, I can say good morning. So let me first apologize and mention that we forgot to say it before, we were very, very happy to start with Julio Parra Martinez from my HES. We're happy to have him all week. And now we continue with Chiara Toldo from Schwarzschild University. So please, the floor is yours.
Okay.
Just one announcement. Here in this part, next to the lectures, we will upload the exercises for the exercise sessions. Okay, so look for them there. And remember that we have 2 sessions in the week, tomorrow and the day after that. So please keep in mind and start looking at the exercises so you can take advantage of the sessions. Thank you.
Okay, very good. Can you hear me, by the way? Okay, very good. And also, can you read my handwriting? Okay, it's big enough. Okay, very much. Okay, thank you very much for the invitation here. It's really nice to be here. It's my second time, like here in São Paulo actually. And so I have decided to talk to you about black holes. So black holes, I believe it's a very fascinating and interesting subject. Because indeed, as you might know, like black holes, like the gravitational force inside a black hole is very, very strong. So it's so strong that even light cannot escape. And indeed, the black holes have an event horizon. So we cannot really see what's inside a black hole, but we know that the gravitational force is very, very strong. And so black holes, in a way that I will explain during these classes, hold the key to quantum gravity. Namely, by studying black holes, we managed to know really how gravity behaves at very, very high energy scales. I decided to tailor my lecture as some sort of a survey of what happens in different black hole regimes. So black holes are very like mysterious objects, and they have different behavior whether you can explore the full phase space, so you can tune the temperature, and you can see how they behave generally at non-zero temperature. They have some enhanced symmetry when you send them close to extremality, meaning when black holes have zero temperature, they have an enhanced symmetry that I will describe. And this allows us to, for instance, count their states via techniques that we developed in the dual field theory. And also, like at the last, I will explain you what it means by near extremal regime. So basically, once you have a black hole and you switch on a bit of temperature, you're very close to T equals 0, but not quite. There is a different set of techniques that actually allow you to compute, for instance, quantum corrections to entropy and to other thermodynamic quantities in an exact way. So in this case, I will give you a bit of a survey of these various black hole regimes and the techniques that we developed over the years. Let's say over the last, well, these come back to the 70s, but these are more recent, for instance, in the past 3 years. So all these techniques that we developed in order to tackle all these issues related to black hole physics. So some of the reference, so strictly speaking, let's say the first and the second class will be about this. I will start very, very slowly, let's say. Then I will tell you a bit about supergravity and various black hole solutions and the microstate counting via holography. And then this will be, roughly speaking, the last 2 or 3 classes, like last 2 classes. So the references for this first class, I'm going to give you here. So for instance, you can see Townsend. And this is, it's called black holes. And you can find it on the archive. Sorry, this is GR. See? But also Dabolkar. Nampuri. Quantum black holes. So I will abbreviate again here, black holes BH. That would be throughout the entire classes. And this is again on the archive. You can find it here, like 08 4814. Okay. So let me start then by saying that indeed, so I regard black holes some sort of as indeed like they can be regarded in a way as the most simple and at the same time the most complex object. So we will see that indeed like a classical version, like a version of classical gravity, is responsible for the fact that a black hole is a very simple, almost structureless object. But instead, the fact that a black hole is very complex is pretty much explained by quantum gravity. And quantum gravity is indeed like this theory, which is still an unsolved problem, like a formulation of quantum gravity, is still an unsolved problem in modern theoretical physics. So black holes hold really the key to that. So a black hole is formed by collapse of very heavy stars. They said when a star becomes of the mass, like according to our latest estimate of 25 to 30 solar masses, a star can collapse. And indeed, once a star forms a black hole, so all the details of the initial star that we had, they are washed away. So we are left with a solution, like a black hole solution, which exhibits an event horizon, and it's characterized only by a few parameters, such as mass, charge, and angular momentum. So in this way, according to general relativity, a black hole is a structureless solution, such as an electron could be. However, a black hole, like as I was mentioning, has also like some thermodynamic properties. So indeed, there is a very, very striking correspondence between laws of thermodynamics and laws of black hole mechanics that tells you that a black hole indeed has entropy. Actually, has like if you compute the entropy of the black hole that sits like at the center of our galaxy, you find a huge number of the order of 10 to the 96. So the entropy of a black hole is much higher than the entropy of the star that actually formed it. And so indeed, in general, this tells you that a black hole is composed by many, many microstates. And to explain these microstates is like the role of quantum gravity. So indeed, like schematically, we'll have that black hole, simple. So this is from classical general relativity. And it is characterized then by mass, angular momentum, and charge. Black hole instead is complex. And this pertains to the realm of quantum gravity. So we'll see that in general, again, black hole is not simple because it's elementary, but rather because it is a thermodynamic ensemble. So we're going to work with solutions to the equation of motion, so to the Einstein's equation, like of, in general, Einstein-Maxwell lambda theory. So we're going to work with solutions of this action here. F mu. For the moment, we're going to set to 0 the cosmological constant. So this action here, actually, like if you neglect this part here, so the solution to the equations of motion, like the static and spherically symmetric, is the Schwarzschild solution that I'm sure you have seen in your GR, like in your basic GR classes. So let's begin with the Schwarzschild solution. So this was found, by the way, in 1916, so more than 100 years ago, by Schwarzschild, by solving the Einstein's equation, which read like this. So if you vary this Lagrangian here, so you set for the moment the gauge field to 0, you vary this with respect to the metric, you get the Einstein's equation, which read like this: R mu nu. This is the Ricci tensor, minus 1/2 G mu nu R equals 0. So if you look for a static spherically symmetric solution to this equation here, you find the Schwarzschild one, which is characterized by this metric here. Can you see if I read all the way here? Okay. So I'm adopting minus plus 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 signature throughout all my lectures. Theta squared plus sine square theta d phi squared. So this is the Schwarzschild solution here. This is this metric. So you have, again, so the time coordinate, indeed, the radial coordinate, and this is the sphere like the two elements of a sphere with angular coordinates theta and phi, the one that you know it pretty well. So first of all, let's just analyze this metric here to see what is the causal structure. So you see that in general, the metric here seems to have, first of all, singularity at r equals 0. So when you put r equals 0, the metric goes up. But also it seems that r equals 2m also makes the metric ill-defined. So it turns out that r equals 2m is an apparent singularity. As we will see in the rest of the class, you will see that actually you can remove this singularity at r equals 2m via suitable coordinate transformation. And at r equals 2m, all the curvature invariants are actually well behaved. For instance, if you contract the Riemann tensor, like two Riemann tensors, you see that it's actually well behaved at r equals 2m. So the real singularity is at r equals 0. And this cannot be removed. It's actually a coordinate singularity. R equals 2m, however, so the first one, the first radial coordinate here, has a special role. So it's not a singularity, but it denotes an event horizon. And you can see, so it is basically a surface that marks the point of no return. Meaning if you fall inside a black hole, if you cross the event horizon, you cannot come back anymore. But so the horizon has a very specific, like determines the causal structure of the black hole solution, and it has some special properties. So now we want to really zoom in into the near horizon geometry. So go close to r equals 2m to see how the black hole geometry really behaves. This is very important because in a lot of let's say, computation that we do, for instance, in string theory or in microstate counting, we do things close to the horizon. We believe that actually the degrees of freedom responsible for black hole entropy reside on the horizon, and thereby studying really how the geometry looks like will give us more information about what's inside. So we want to see what is the near horizon geometry of the Schwarzschild solution. So we zoom in the near horizon geometry. So we define a parameter, the psi, which we take to be very small, which is like the difference between the radial coordinate and 2m. 2m is the Schwarzschild radius here. So by doing this coordinate redefinition, we get that the two-dimensional metric, which is this one, behaves like this. Where I use the shorthand, the omega 2 squared, for indicating this metric here. Just a minute. Okay. Then from here, we redefine the coordinates. So we introduce another coordinate, which is rho squared, which is 8m psi. So it's another, so unfortunately for this first 40 minutes of the class, there will be lots of coordinate transformation. But we do it for a purpose, because we need to see what is really the physics of these near horizon geometries. So we introduce this coordinate here, and then we get that the line element close to the horizon is this one. So this is the line element that you get in the near horizon geometry of Schwarzschild solution. And you see that up to here, it's like completely regular, actually. Yes?
The lower orders in the spherical part of the electric?
Yes? This is just...
In the
okay. 2m squared.
Yeah. There are lower, higher orders in that, right?
Yes, there are also, there are higher orders here, but you will see that just at the zeroth order, you have that this is just a two-dimensional sphere constant.
I mean, yeah, that's the question. Like, those orders doesn't matter. Like,
For the moment, doesn't matter, let's say. Yes, if you redo this coordinate transformation here, you will see that this is like a finite geometry, which is the product of the two spheres, and this is two-dimensional Minkowski space written in Rindler coordinates. So I took, like here is just, like the matrix that I got here is just the product of two finite parts, sphere and this one. So I didn't keep track here of the sublinear terms. So this is, for this one, you have S2 with constant radius. And this one is two-dimensional Minkowski space in Rindler coordinates. So how to see this? So we all know Minkowski space, right? So we are going to do a chain of coordinate transformation to see that we can take Minkowski space and we can put it in this form here. So then this tells you that indeed close to the horizon, like the Schwarzschild matrix doesn't have any pathologies. It's just flat space times a sphere. Sorry, this is a two-dimensional Minkowski space in Rindler coordinates. So it's a particular kind of coordinate that is like relative to an observer which is accelerating. Now I'm going to show you how to get this form for Minkowski 2 from the usual Minkowski space that we all know. So we start from 2D Minkowski space. This form is, of course, very familiar to all of you, right? This one. So we need to do a chain of coordinate transformation. First, we define, bear with me, we define t plus x, v equals t minus x. So then the line element becomes ds squared minus the u dv, okay? And then we further change coordinates. U equals 1 over, like, k is for the moment an unknown constant. You just leave it here. E to the k u. V equals minus 1 over k e to the minus k v. And I take this element here, it then becomes minus e to the k u minus v du dv. Again, I have to make another coordinate transformation. We are almost there. Again, so this equals e to the 2kx minus dt squared plus dx squared. So we have seen that doing first this coordinate transformation, then this, spit out a factor in front of the metric. And by further redefining rho equals 1 over k e to the kx, we get the metric in the desired form. Well, let me just put it here. Minus rho squared k squared dt squared plus d rho squared. So if you see the similarity that we have from this formula here to this one. So we have started from Minkowski space. We're going through all these coordinate transformation here, chain of coordinates, and we got to this formula here, which coincides with this if we define k equals 1 over 4m. By the way, in all this lecture, I will set g, the Newton constant, to 1, just to not bring it around. But otherwise, you will need to reinstate it first again in the Schwarzschild metric that I showed you before, 2gm, but I set g to 1. So this kappa here, let me just write it here, kappa equals 1 over 4m, is called the surface gravity. Which is, roughly speaking, like, well, you can do the computation, you can show it as an exercise. That is the Newtonian acceleration that is felt by an observer at the horizon at a radius r equals to m. So this will be a very important quantity. So it's a quantity that really is related to the horizon itself. So in general, so the takeaway from all of this is that the Schwarzschild solution has some singularity, which is at r equals 0. It has an apparent singularity at r equals to m, but in general, the horizon, like, is not singular at all, but actually is just two-dimensional Minkowski space times a sphere. We will see that this will be very different with respect to, like, when we will deal with extremal or some other kind of black hole, like Reiser-Nostrom extremal black hole. The near horizon geometry will have a very different form for this one. But so now, there is something special going on at r equals to m. As I was mentioning, it is the horizon of a black hole. And in order to do so, we need to go through some other coordinate transformation, and we have to draw some diagrams, which are called the Penrose diagrams, to really understand what is the causal structure of these black holes before going on and talking about the thermodynamics. So first of all, let me introduce some other coordinates. I warned you that there were lots of coordinate transformation in this class, but I swear we're going to use them later on. So for the full Schwarzschild solution, one can act somehow in the same way. We can introduce some other sort of coordinates that show that the metric is regular at r equals to m, which is called the tortoise coordinate. Which is defining r star. So in this way, like once we define the coordinate in this way, the two-dimensional form of the Schwarzschild matrix, so now we're going to do this to the full Schwarzschild solution, looks like this. Where I left just for the moment, so the coordinate transformation is between r, the r of the Schwarzschild matrix, and this coordinate r star. So in this, I just wrote here just the two-dimensional matrix that is like the TR component of the Schwarzschild solution. And I left this r here just out for the moment. So we can go back now at the Rindler coordinates that we used before. We do the same thing. I'm just gonna write it down. Not gonna do it in more details, but we're gonna again define u and v. and also big U and big V as before. For M. So the Schwarzschild-like metric becomes like this. Sorry, these are small u and small v, and this is big U and big V. So this is just a two-dimensional element of the Schwarzschild solution, and even here we see that, so we have applied this tortor coordinate and then these Rindler-like coordinates to the full black hole geometry, focusing only on this two-dimensional element. We see that there is nothing wrong at r equals to m. Also from the full geometry, you see that this is fully regular. And so this is the so-called Kruskal extension of the Schwarzschild metric that really allow us to go beyond, actually to see that there is nothing that goes wrong on the horizon of the black hole. However, globally, it is a special region, because it's really the horizon, so it has some, it brings something to your causal structure. So in general, we can see that, so from all this coordinate transformation, we can have a few observations. So I might have erased some of the formulas that I use, but you have written them down, so I can just, I don't need to repeat them. So a few observations. So first of all, so constant radius surfaces rho squared equals 1 over kappa squared e to the 2kx equals minus uv constant. So in general, the constant radius surfaces in the Schwarzschild solution are hyperbolas. So this is constant. This is minus uv equals constant. Are hyperbolas in the u and v plane. And then, so from the, let's see, from this formula here, we see that trajectories r equals to m are light-like. So u equals 0 is the past event horizon. That's what we call it. And v equals 0 is the future event horizon. So it is very useful at this point to draw all of these in a diagram. And I'm gonna probably, yeah, I can put it here. In general, we can draw what is called the Penrose diagram. So once we have introduced these coordinates here, in which basically the line U equals 0, like the line V and U, they are tilted with respect to each other at 45 degrees. But so U equals 0 and V equals 0 are these. These are the two horizons of a black hole. So the singularity is at R equals 0, which is both here and here. And this is, in general, the outer space of the black hole, which is just the black hole asymptotes to Minkowski space. So in this quadrant here is asymptotically Minkowski space. It's the outer region of the black hole. The horizon of the black hole, the future horizon, like here. And the past event horizon is this one. And this is singularity, which in this case, a Schwarzschild is space-like. So it means that if you go inside the black hole, so in this diagram, like the time-like observer, like they are within the light cone. So basically, the lines are like light cone is this one. Time-like observers, they go like inside the cone here. You see that if you enter the event horizon like this one, you're bound actually to encounter the singularity, because you cannot, in order to exit, you will need to travel faster than the speed of light. So, okay, this is just, let's say, so then we are all on the same page about the causal structure of a simple black hole such as the Schwarzschild. Of course, in what follows, for instance, for the thermodynamics and for other aspects, we will deal not only with the Schwarzschild black hole, but also with black holes with charge that live in spaces with with a cosmological constant. But pretty much with similar coordinate transformation, you can draw these diagrams for all sorts of black holes. And this gives you an idea of what really, like, how are the light trajectories, how are the observers, the hyperbolas like these are observers of constant radius, so on and so forth. So now that we have made sure about, like, let's say, set the ground for the causal structure, now I'm gonna pass on to the thermodynamic, let's say, behavior of black holes. So indeed, once people understood that indeed you have a singularity which is shielded by horizon and so on and so forth, people started studying all the various black hole solutions, and they discovered a very remarkable properties of black holes, namely that, as I was mentioning, laws of black hole mechanics, they really are in parallel with laws of thermodynamics. So in principle, this was something unexpected and surprising, because there was no a priori, let's say, reason why these two things should be the same, why space-time should know about statistical mechanics or thermodynamics. But this is like this is something which is indeed very fascinating, and something that is not just an analogy, but really it drove like the development in like, for instance, like it inspired the holographic principle, the SCFT, and so on and so forth. So it's something like, it's a very deep notion, it's a very deep concept in black hole physics. So indeed, like people can draw, like scientists, starting from the work of Bardeen, Carter, and Hawking in the 70s, draw parallel between these two, like between, let's say, black hole mechanics and thermodynamics. So for instance, for like, so the zeroth law states that in this, for stationary black holes, the surface gravity, which is the quantity that we have found that we call kappa, that enters into the Rindler, like the Rindler description of the near horizon geometry of a Schwarzschild black hole. So the surface gravity is constant at the horizon of a black hole, of a stationary black hole. So surface gravity kappa is constant at the event horizon. Of black hole. And this happens also for instance, for black holes which are spinning, for which the horizon is slightly squashed. The surface gravity still stays the same. On the other hand, this is paralleled on the concept of, like, in thermodynamics, in a way that at equilibrium, the temperature of a body is constant throughout the entire body. Okay, this is easy. The one that is a bit less, requires a bit of work, is the fact that indeed, so there are also the first law of black hole mechanics reads this way. So if you have to change a bit the parameters that are on your black hole, you see that so black hole is specified by mass, charge, angular momentum, and also their conjugate quantity. If you modify them a bit to find another solution, so you find another solution, but the parameters need to be related via the first law, which states that indeed, like a variation of energy is equal to kappa 8 pi delta A, where A is the area of the event horizon. And then we also add the other quantities, which are charge, variation of the charge, and this is the quantity, the chemical potential, which is conjugate to the charge. And again, similarly, omega delta J. This is the variation in angular momentum, and it's multiplied by omega, which is the angular velocity at the horizon. This is the conjugate quantity, the quantity conjugate to the angular momentum. At the same time, like the parallel in the thermodynamics is that energy is indeed conserved. So you have the formula, which is delta equals TES plus mu dq plus omega dj. So that's very, like, you see that they are super, super similar. Here, I should have probably put, instead of E, I put M. But in general, it's, so the mass of the black hole is really the energy available to the system. But okay, to be precise. And then we have, finally, second law, which states that indeed, like, the variation in the total area of black hole is always positive, right? So for instance, if two black holes of mass M1 and M2, they merge into each other, you get basically the black hole that you get will have the area which will be like bigger than the sum of the areas before. So you have that if a black hole of mass M1 and M2 merge, due to the triangle inequality, you have that the area of the black hole that results is always bigger or equal than the sum of the single area of the event horizons. And this is because, in general, if you remember, in front of the sphere part, we have the mass. So the entropy of each one of the black hole is proportional to the mass squared. But when they merge, they will have mass, which is M1 plus M2, and hence the entropy will be the mass M1 plus M2 squared. And this is parallel in the fact that the second law of thermodynamics says that the entropy in every physical process, the entropy is never decreasing. So delta S bigger or equal than 0 in physical processes. So this analogy between laws of black hole mechanics and thermodynamics indeed was due to Bardeen, Carter, and Hawking. And it was due to Bekenstein, the fact that, so Bekenstein had indeed the idea of associating to the area of a black hole horizon an entropy. And indeed, this was motivated by the fact that indeed, so in a system, entropy should always, like, imagine the universe plus a black hole. The entropy should always, like, at least increase or at least remain equal. So imagine that you form a bucket of, like, you can get a bucket of hot water and you throw inside a black hole. If the black hole has no entropy, it will mean that basically you have actually decreased the entropy of the entire universe. And this is really not correct, not consistent with the laws of thermodynamics as we know it. And so the black hole, like Bekenstein thought that, okay, maybe actually the black hole, so if you indeed throw in mass or this bucket of hot water in the black hole, its mass will increase, and eventually also the area of the event horizon will increase. Maybe this area of the event horizon is actually what is the entropy for the black hole. And this was actually corroborated. So if a black hole has entropy, also, like it's a thermodynamic system, so it should also have temperature. In particular, the temperature and the entropy of the black hole, they are related by the fact that indeed, so 1 over T equals to delta S, sorry, delta M over delta S. Sorry. Just to make it very clear. Okay, delta S over delta M. So if an object has mass and has entropy, the variation of the entropy with respect to the mass gives the temperature. And actually, Hawking showed that indeed, by taking into account quantum effects, a black hole has radiates at a purely thermal spectrum, which has with a temperature which is equal to the surface gravity, or say proportional to the surface gravity. So indeed, we have that then black hole radiate at temperature equals to h bar k over 2 pi. And for a Schwarzschild black hole, this is equal to h bar over 8 pi m. Pi m. So this is basically, it's a quantum, like you can retrieve this formula, so you can read off in Hawking original paper, but it's basically like we can come to this result here by basically checking, like doing quantum mechanics on a fixed black hole background. And this is due to the fact that, indeed, the vacuum that is observed by someone far away is not actually vacuum for an observer close to the horizon. And so this discrepancy is embodied in the fact that a black hole really, as a quantum effect, radiates indeed at a temperature which is equal to this formula here. So in general, so we have seen, so I invite you to read this paper here, which I think is pretty nice, that really tells you how black holes really radiate. But so the upshot of all of this first part of the class is to tell you that indeed, so a black hole has an event horizon that shields the singularity, and this event horizon has some thermodynamic properties. A black hole has mass, charge, angular momentum, but also also has entropy and also radiate at a temperature, which is proportional to the surface gravity. In general, if you believe, statistical mechanics was the Boltzmann law, like the entropy of the black hole should have a counterpart in terms of the degeneracy of states. So this is something that you have seen, for instance, in your statistical mechanics class. So the black hole entropy should take into account the degeneracy of the states inside the black hole. That's why it is very important. So part of the classes that we're gonna have will be devoted to really explain what is the degeneracy that forms black hole entropy. So, okay, but now in the first class, we're not gonna do so much of microscopic, then we're gonna just play a bit with all these beautiful formulas that are here. And it's something that you can do, because in general, black holes, as thermodynamic ensemble, they can also undergo phase transitions. And this is something very nice and very, very tantalizing, especially if you are, for instance, in asymptotically ADS space. Because as you might know, there exists a correspondence between indeed gravity in ADS space and conformal field theories. So you can use, for instance, phase transitions of black holes to model something in the dual field theory. And the thermodynamics of black holes is particularly rich. So you can have different black hole states, different black hole branches, and phase transition between them can arise. So what is a phase transition for a black hole? Well, that's what I'm going to explain you in the next 20 minutes. In particular for black holes which are in anti-de Sitter space. So I'm going to give you an example of phase transition by using the laws of black hole mechanics that are there. So during this class and the next class, I will tell you many different examples of phase transition. One of the phase transition will also, you can reproduce, is also going to be left as an exercise, but we can do it all together. So let's say, phase transitions. Like a nostrum black hole in ADS space. So the first example of black hole thermodynamics and phase transition that I'm gonna talk about will indeed concern black holes in ADS space. So ADS space is a space that arises as solution, like as a maximally symmetric solution to the Einstein's equation with a negative cosmological constant. And it's of fundamental importance for the ADS-CFT correspondence that I am sure that most of you are familiar with. But so thermodynamics in ADS space is particularly rich because in general, the fact that you have a negative cosmological constant makes your space to act like a box. So basically, your potential increases at infinity and keeps the radiation in, which means that several different black hole branches can be in equilibrium with each other, and phase transition among them can arise. So we're going to deal with black holes, which are solution to the action, which is this one. So I also wrote it down before, but let me repeat. Okay, G is equal to 1, square root of G, R minus F squared minus lambda d for x. So the equation, if you vary this with respect to the metric and also if you solve the Maxwell's equation, the solution that you get is the Reisner-Nostrom anti-de Sitter black hole, which is characterized by this metric here. So with respect to the Schwarzschild solution that we had before, we have now a solution which has, first of all, it has electric charge. So I forgot here to write also the solution for the field strength. So the solution is supported by a gauge field. I wrote down here the field strength, and the metric, which is this one. So if you just neglect these two parts here, this and this, you recover the Schwarzschild solution that I wrote in the blackboard before. This part here is due to the fact that you have a cosmological constant. And lambda is negative, so this part here is positive. So this is really the potential that grows towards the asymptotically R goes to infinity. And the fact that you have charge is really materializing to this piece here. So this is a solution to the Einstein's equation, which is indeed static spherically symmetric, which is supported by this gauge field here. So the temperature for this solution, the Hawking temperature of this solution, you get it from computing the surface gravity at the horizon. And I can give you the formula here for comparison. You can derive it as an exercise, but in general, you will have this one. So as also here, you have mass is the mass of the black hole. Q is the charge. The temperature, you compute it as a surface gravity. So you have to basically compute the derivative, the first derivative of GTT, and evaluate it at the horizon of the black hole. So for all these black holes, whenever you have charge or also angular momentum and so on, you might have different non-coincident horizons. So for the Schwarzschild solution, you have only one horizon, because you have to solve this equation equals 0. But here, in general, you have to solve a fourth-order polynomial. So you will have, in general, many different solutions. The surface gravity, you evaluated like the surface gravity as at the outer horizon, because it's the one that you really care about. So this solution here satisfies the first law of thermodynamics. We neglect this part for the moment because you don't have, this is a static solution. You don't have any angular momentum. And so we're ready now to see the phase transitions, at least compare how many branches of black hole solutions are there. So first of all, what we need to do, like as in general, in every statistical mechanics, thermodynamic system, you fix your ensemble. So you have to figure out what, like in your system, what you want to keep fixed and what you want to vary. And in this case, we work in the ensemble, in the canonical ensemble. And in the black hole case, which means that we fix the temperature and also we fix the charge. So what we want to do now is to see whether there are multiple black hole configurations. Yes? Temperature is, so here probably I should have, so it's the derivative of GTT. GTT is this one, computed over 4 pi, computed at the outer horizon. It's something that I skipped a few passages, but this is what you get if you try to redo it with Rindler coordinates, the near horizon geometry of this black hole. Yes, I put all, so for now on, yeah, G, H bar and so on will always be equal to 1. So this is just the full solution that you get. So this is generic R. The one that will appear, okay, I erased here. When you, so you know in the black hole, like in the first law of black hole mechanics, you have delta M equals, like, and let's say mu is defined as Q over R plus. But for the solution now to be a solution, this needs to be generic. So this radius is just a normal coordinate. This is just a metric that depends on R. These are just quantities instead that's just like you plug in numbers and parameters.
Last slide. Yeah, it's like fixing the temperature is like fixing the Q?
No, for the moment, so I'm going to explain you this, what it means. I'm going to, so we want, so by this, I mean that we want to consider solutions which have same temperature and same charge to see whether there are many of them or it's just one. So if there are many of them, there can be a phase transition between them. The one with the lowest free energy wins.
I'm thinking like in the zero law that you wrote.
Yes, yes.
In that case, like the signal of the temperature in the thermodynamic case
Yes,
is equivalent to the surface gravity, right?
exactly, yes.
So in the canonical ensemble, shouldn't it be like just fixing the surface gravity mathematically?
I don't, sorry, can you repeat that? Because I don't think. So the surface gravity is always constant at the horizon, and this defines the temperature of the black hole. But then, depending on how, like, on the parameters, you can put here, you know, different values, the parameters. Your black hole will have a different temperature because the parameters will trickle down here, right? So you want to see, I'm going to make a plot now, so then I think it will become clear what I mean by having the same temperature, if you want. But yeah, so basically, you will see that for a certain temperature, you will have more than one configuration. That will what will give you the phase transition. Let me just write it down now, make a plot, and then you'll see what I mean. So what we want to plot is that we want to plot the temperature versus, for instance, the entropy of the black hole. Temperature versus entropy. And we are going to deal with two different black hole regimes. So one is the regime where Q is less than a critical value. And the other one is where Q is bigger than a critical value. So in this case, you have that. So this is the behavior that you get for Q, like for a large amount of charge. the entropy in this formula is, so let me write it down here, black hole, equal to, let's say, 4 pi r plus squared over, I think it's something like, I think the formula is like pi r squared. So basically 4 pi r squared over 4. Yes, the dependence on Q you have inside R plus. Because to get R plus, you need to solve this equation here. You need to solve for the work factor is equal to 0. So all the dependence on the parameters R plus and so on will depend on mass, charge, and also cosmological constant. Also, that's what I'm going to tell you. So basically, you have that for a large amount of charge, you have that the temperature is a monotonic function of the entropy. So the entropy is this one. The temperature, you compute it via this one. If you choose a value of Q, which is very, very high, in let's say, units of the cosmological constant, you say 300 or so on, you have this. But if you lower the charge like smaller than a certain critical value, you have a plot which resembles this one. So in this case, you have fixed a charge. You also fix the cosmological constant. But all these solutions here have different values of the only parameter which is left, which is the mass. Okay? So now you see that if you are within this range here, this here, you have up to 3 solutions, 1, 2, and 3 solutions, which have the same temperature, different mass, and the same charge. And this is what I mean, that these 3 black hole branches we will be able to have a phase transition between them, because we fixed the ensemble, so we fixed the value of Q. We fixed T, because all these 3 configurations have the same T. You see, they have the same coordinate here, but they have different values of mass. The fact that they have different values of mass, they have different values of entropy as well. But we named this as small black hole, medium, and large black hole. So this is just the value of QC, okay, so the value of QC will depend on the value of the cosmological constant. I have a formula for you, but basically, so QC goes as 1 over square root of lambda, so it depends on the value of cosmological constant, and basically at QC, you have that the temperature will have all these 2 minima and maxima become 1. You have a critical point, basically. You have a discontinuity in the first derivative. So in this case, this is the boring case, meaning for every value of temperature here, you have only 1 black hole solution, right? This is a monotonic function. So this is the boring case. This is the more interesting case, where you have different branches, and then the phase transition can be here, can happen. Exactly, yes. I'm changing M. Or equivalently, I'm changing R plus. So this would be subject also of one of your exercises. With Mathematica, it's a 1 line of code to get this one. So it's very nice. If you have Mathematica, we can do it all together. I think it's something that comes out very naturally. By the way, this is something that it's a very, very famous paper. I don't want to claim the result as mine. By so Chamberlain, Johnson, Myers, and Emparan in '99. And the same phase transition you have also for black holes which are rotating, but we can leave it to another story. So we have seen that this is a very good scenario. If we take the charge to be much less than Q critical, we have something that goes on here. So in order to see, so we have 3 different configurations, and in general, in thermodynamics, the configuration that has the lowest free energy dominates the ensemble, right? In general, that's what you have in normal like thermodynamics. And in order, so since we are in the canonical ensemble, we fix temperature, we fix Q, the quantity that we have to extremize is the Helmholtz free energy. So this is your thermodynamic potential, Helmholtz free energy. F equals m minus Ts. This is your thermodynamic quantity that needs to be extremized to find the configuration that wins the ensemble. So if you plot this thermodynamic potential, I'm almost done. I think I need five or 10 more minutes, but then we can get to the end of this. So if we plot this thermodynamic potential, in this case, okay, I figured, okay, I should have, okay. So, okay, we can go a bit slower then. So this is the Helmholtz free energy that you will see also, yeah, in general, once you have the canonical ensemble in just normal thermodynamics, this quantity here needs to be extremized. It's also a consequence of the fact that the first law needs to be satisfied. You can do like the proof is just in one line, basically. And so if you compute the free energy for this, so plot free energy versus temperature. Here, once again, it's a very boring graph that is monotonically in T. Also, in general, the slope here is negative in such a way that indeed, like, it's a well-defined thermodynamic system. Things are very different in this case here. So this you can do it with Mathematica. Like there is a command that does it for you, but then we're going to do it in the exercise. But in general, what you have here is that the first branch goes here. The medium branch is here. And the large branch goes here. Okay? So the first branch is the small one. It goes all the way here. The medium branch is this one. And the large goes all the way here. Okay? So in your thermodynamic ensemble, you have to extremize this thing here. So it means that the configuration with the lowest free energy wins. And in this case, it means that you have to follow this line here up until this point. But from this point onwards, then you have to follow the other line, right? This one. So it means that at this point, you have that the small black hole gives space. They're not thermodynamically favored anymore. So you have a phase transition between small black hole and large black hole. So this is just from plotting this graph here. So let me make a few observations. Yes, exactly. So, so the small one up to here, let's say, so the small goes up to here, medium up to here, and so on. So the small one are this. The medium one are this. And the large one go all the way from here to down. I mean, this goes on, and this also goes on further down. It's not the bottom, so it will be, okay, this is something from later, but it will be exactly at the time in which this area here is equal to this area here. But we are gonna do it later. So, okay, let me just recap a bit what we got from that plot. So as a recap again, so we have played a bit around with the Reister-Nordstrom black holes in asymptotically ADS space. Yeah, of course.
If you change the ensemble, could you do the similar thing?
It's left as an exercise. But yes, no. So basically, whenever you have like a, let's say, whenever you have a phase transition or an instability in your system, the physics intuition is that even if you change the ensemble, you will still get some instability and so on. The fact is that you will need to compare different kind of solutions. So if, for instance, you can, now we choose to work in the canonical ensemble where you fix the temperature, you fix Q. But you can choose, for instance, the grand canonical ensemble where you fix T and you fix the chemical potential. At that point, though, so here, this plot, I made the plot in such a way that I kept Q fixed. When you keep fixed the chemical potential, there will be other solutions, for instance, a gas of gravitons in ADS, that will also play a role in an ensemble. So the phase transition will still be there, but it will be a phase transition between a gas of gravitons with some chemical potential and some charged black hole. But we can study it in the exercises. In the same paper, they also study the grand canonical ensemble. So bottom line is that you will still have a phase transition, but between different states, let's say, because your ensemble also has other solutions if you change the boundary conditions. But
Sorry.
yes.
Silly question.
No.
But how is it that there can be a phase transition between small and large if you have to go through medium in between?
Good.
First process?
Yeah, that's a good answer. The point is that, so in general, so from this graph here, you see that basically you never go through the medium ones because your phase transition between small and large. I didn't tell you something in the first one, is that by looking at the slope of the T, of the graph T versus S, the slope of this configuration here gives you the value of the specific heat. So basically, these medium black holes have always negative specific heat, so they are unstable, and they don't appear as physical solution. They never appear in the thermodynamic ensemble. So in a way, we knew that since these were unstable, they were bound to never be dominant in your ensemble, let's say. But yes, it's something that you still see them in this graph, but then you know that they're not the ones that are good ground states of your system.
Yeah, so basically instead of going through the medium, it's going through the phase transition.
Exactly. It's like, yes. So, yeah, you're anticipating it a bit. So this reminds a bit of the van der Waals phase transition. Well, I'm gonna draw it later. But in general, it's also why, like, yeah, in this, basically, on this line here, which is this point here, you have coexisting of small and large black hole as you have coexisting of a liquid and gas phase in the van der Waals diagram, let's say. So bottom line is that the medium black holes, since they have negative specific heat, they never appear in your thermodynamic ensemble. Other? Yes. This thing is like this is a first order phase transition because you have a discontinuity in the first derivative of the free energy. So whenever, so if you had to kind of raise Q towards its critical value, so instead of having Q smaller, you have Q equal, then this thing will reduce more and more and more, and then you will have all the way a second order phase transition at the critical point. So it will look a bit like this, but it will have some sort of small kink, like small inflection point, like, okay. So any other question? Okay, let me then recap a bit to see what we have found. So some of you also like anticipated my observations, but that's it's very good this way. So let me just comment on this. So just, okay, observations. Okay, first of all, so as we mentioned, medium black holes always have negative specific heat. Medium black holes have negative specific heat, so the specific heat is defined as this one. T ds over dt at Q fixed. So in general, you have that they never appear. As we mentioned, they're always non-dominant in your thermodynamic pictures. And let's see what else. So in general, we can also plot a graph of our phase space, let's say like so some was really based on your observations, of course. So you have that, okay, maybe this is like a bit tilted. So if you plot Q versus T, you have that at some point at Q critical, so you have a phase transition between small and large black hole for Q, which is smaller than Q critical. When Q is bigger, like starts from Q critical and it's bigger, then you have, instead, you have a crossover. In general, you have like just one configuration. These are all, if you want, only big black hole, like large black holes, that keep on being just stable. They don't transition. They don't do anything. While for this one, you have indeed a phase transition between small and large. The location of the phase transition, so the coordinate here, this T, let me just, here, T, which I call T of phase transition that you have here in this graph is at a coordinate such that this area here is equal to this area here. That's what happens. And this should probably remind yourself as the van der Waals like a picture of like, let's say, for the equation of state for real gases. That, if you remember from your thermodynamic classes, look like this. You have to plot the isotherms for a temperature which is larger than T critical, bigger than T critical. Here, you have the isotherms are just hyperbolas in the PV plane. But then, if you go like just lower in temperature, you have that the isotherm starts looking like this. So for T, bigger and smaller than T critical. And once again, you have that also at this, the phase transition, like you have the liquid phase, which is like, let's say liquid phase is this one. And then you have a gas phase, which is like here. And along this line here, in this range here, you have coexistence between liquid and gas. And again, to find this pressure here, you need to compute the area. So you need to find the pressure in such a way that you have that this area is equal to this one. Now I put it in a bit, okay, maybe here. So that's why from this sort of phase transition, so we call it like small and large phase transition, but also the authors themselves, they call it a liquid gas-like phase transition because it shares a lot of properties of the liquid gas phase transition that you have in the van der Waals system. So you see around how playing around with black hole thermodynamics, something very important in GR and so on, we have recovered actually water. So it's something very, So you can model a lot of different phase transitions with black holes, and this will be also object of some of the other classes. And they all entail choosing your ensemble, so choosing the boundary conditions in which you find your solutions, and then see which one indeed dominates your ensemble, and basically plotting the appropriate thermodynamic potential and finding the solution that minimizes this potential. So in general, yes, you can also change the ensemble, as you mentioned, so on and so forth. So let me see if I have something else to add. Yeah, I think that for the moment, this is all I have to say. This is the first example of the phase transition that we have found. Then maybe, yeah, in the next classes, we're gonna explain a bit more. But this is somehow the prototype. Okay, another observation that I have to say is this. So in this graph here, so some of the exercises that I have devised, basically, in some of the exercises, you will see what really means to have negative specific heat for a black hole, what is the instability, and so on and so forth. But let me just mention that these three black hole branches have a specific meaning in terms of they are a consequence of the fact that you are working with charge configurations, and also you are working in anti-de Sitter space. For instance, if you work in asymptotically flat space, the large black holes are not there. So you find only two branches. You find the small and the medium branch. In particular, the medium branch, which would correspond to the largest black hole in Minkowski space, they are unstable. While if you don't have charge, magnetic or electric charge, but you have ADS asymptotics, you don't have this part here. So the fact that you have small, medium, and large is due to the fact that you have charge and also negative cosmological constant. For the Schwarzschild solution, you have only one branch. So you don't have charge, you don't have cosmological constant, you have only the medium branch. And that's also reflected in the fact that the Schwarzschild solution in Minkowski space has negative specific heat. This is something that you will see also, I think, in one of the exercises that I give you. Yes? Yeah. Okay, good. So, I mean, with angular momentum. Yes. So yes, you will have a very similar picture. So if you have like if you have a Kerr black hole, so in ADS space, you will have a very similar picture, similar to this one. If J is lower than a certain critical value, that also depends on the cosmological constant. This one, this will also, so rotating black holes are also very important because a lot of, let's say, lots of results on microstate counting, they are available for rotating black holes. But the phase transition were studied by Cognola, Caldarelli, Cognola, Clem, I think shortly after, I think in the same year. They discovered that basically the same phase transition that goes on in the case of a static black hole, you can have for rotating and also rotating charged black hole. They undergo pretty much a similar phase transition, let's say, once you lower both the charge and the angular momentum below a certain threshold. So this is something that you see. And if you work with higher dimensional black holes, for example, black holes in ADS 6, ADS 7, you can have a different variety, meaning that the temperature can have something like this. You can even have more ground states, more branches, and your phase, let's say your free energy can also have different kind of branches, different phase transition based on where you are. And this is due to the fact that indeed you have different, the warp factor is not a 4th order polynomial, but it becomes 6th order, 7th order, so you have many more branches. But of course, we deal here with black holes in ADS 4. Most of these things will be restricted to 4 dimensions.
If you have questions, please raise your hand and I will hand you the microphone.
Yeah, maybe I should have repeated the question.
Do
Yes.
you have something more to say, or do we shift to question and answer?
Yeah, we can shift to questions. Maybe, yeah, because.
Thank you very much for the lecture. What I would like to ask, I may be getting a bit ahead of your plan, so I apologize for that. But what I'm curious about is that, as you mentioned, Schwarzschild black holes usually have negative specific heat, and in here we're getting black holes with positive specific heat. And when dealing in asymptotically flat spacetimes, we have the phenomenon of black hole evaporation and eventual disappearance. Does this mean that in ADS we can get black holes that do not evaporate?
In general, what happens for ADS is that you have this the black hole potential. So naively, so the Newtonian potential you get from the derivative of the GTT term in your metric, right? Given the fact that you have a term like the warp factor contains a term minus lambda over 3r squared plus 1 minus 2m over r plus q squared over r squared. So the fact that you have in ADS, you have this term here, you have a potential that grows at infinity. And this is really the origin of the fact that your ADS space acts like a box. So it keeps the radiation of the black hole inside. That's why you can have black holes which are in equilibrium with radiation at the same temperature, let's say. That's why a lot of computations that you see, for instance, about the page curve and so on, they are in ADS too, but they have to allow the radiation to escape. That's why they connect it to an asymptotically flat region.
I see.
So in general, whenever you are studying evaporation of black holes, and you want to see how really radiation escapes, ADS is not a good setup because it keeps the radiation inside, basically. Like it acts like a box.
I have a dumb question. The slope in the phase graph means that for lower charges, the transition happens at a different value of the charge or the temperature,
yes, yes.
right? Okay.
Yes.
Yeah. Okay. Yeah, that was it.
So it's like in general, that's I think that's what you get empirically by lowering the charge here. You see that the temperature at which you have the two areas,
It's
varies
a
a
different
lot.
one.
Varies a bit.
Yeah.
So I
Thank
think
you very
this
much.
is something that you get it from. If you plot it with Mathematica in general, you can sample and you see.
Thank you for the lecture. So in this case, you do not have a transition into pure ADS?
Sorry?
In this case, you do not have a phase transition between the black hole and the pure ADS space?
Exactly. You don't have that because we have chosen to be in an ensemble of fixed charge. So, so if you had ADS space plus charge, if you don't have a mass, you have a naked singularity. So I don't want to allow, I want to allow here phase transition among solutions which are regular, that do not have a naked singularity. So this means that you always need to have a mass, which means that ADS plus charge bare is not allowed. It will be allowed, though, if I fix the chemical potential. Because by fixing chemical potential, I could have a chemical potential even without actually having like an actual charge. In that case, ADS plus a gas of gravitons is allowed. And then you will have to redo this plot, and we can do it either next time or as an exercise. You will see that there exists more like a Hawking page-like phase transition. But yeah,
Okay.
That's pretty much probably what
Thank you.
meant.
I have just one more question. So in the extreme points of the TS plot, you have an infinite specific heat, right? Because, I don't know, dt, ds goes to zero?
Yes.
That has something, some interesting physical interpretation on the black hole point of view?
Yeah, that's a good answer. I mean, yeah, this happens. I remember talking with a lot of my colleagues about that, but we didn't find anything that is particularly illuminating about that. But yes, that's true. If you plot the specific heat, yes, you get these tails that diverge. I don't have a very satisfactory answer at this moment.
Okay, thank you.
They don't seem to be pathological, at least for that. But
Hi there. Thank you for the class.
I was wondering, I saw this phase space graph that you put in the board. It's a very naive question. So can you build a model of a crossover? Can you really do that with these black hole things? Can you have a model that instead of give you first order or second order, it's actually have this crossover?
So the crossover, I mean, I called it crossover, meaning that there is no phase transition.
Yeah.
That's what happens here, basically, because here you have your black hole that continuously changing from being small-ish. I mean, here you have Q bigger than QC, so basically, you will have the black holes that you have here. They will always be large, let's say, compared to the ADS scale. Also, they will always have positive specific heat. So the crossover, what I called here with crossover, I called it like I meant like a solution which can smoothly grow without undergoing any phase transition.
There is no critical point.
No, exactly.
Okay.
So and that's why you have it for Q, which is bigger than a certain threshold, and you have it all the way up here, let's say.
Okay, thank you.
For further questions, I have to say that that clock is incorrect and that clock is good. So we have still 5 more minutes for questions. So don't be shy.
Okay.
Sorry if this is a basic question, but why is the temperature related to the time component of the metric tensor?
So do you remember that so what I put in the first part of, allegedly I should have probably explained better, but do you remember like in the first part of the class where I told you basically that you can find this, you have a coordinate transformation that takes you from the near horizon geometry to Rindler space, where the surface gravity appeared. You remember that there was this constant K appearing in the Rindler rewriting of the near isometric.
Yes.
That K, you get it exactly from differentiating, so from taking the derivative of the GTT factor in the metric.
Okay, so then you...
So it's a way to extract the surface gravity, and you know that the temperature is proportional to the surface gravity, so that's how you get the connection.
Okay.
But yes, there exists, like whenever you have to compute the surface gravity of something, in general, you differentiate the GTT component, and then you evaluate it at the horizon. This gives you the surface gravity.
Okay.
And then you can get the temperature.
Yeah, get all this. Okay, thank you.
Yeah. Oh, there's another question.
Oh, sorry.
Professor, could you say why the plots of temperature of an entropy doesn't start in 0?
Exactly, yes, good question. So, yes, because this doesn't start in 0 because at temperature equals 0, you will have the extremal solution.
Okay.
So, okay, it will be a solution that I meant to talk about in the next class, but it will be the solution that arises when two of the horizons, so if you take the solution of the work factor equals 0, these are the horizon, when two coincide, you have an extremal solution, which has 0 temperature, but still has non-zero entropy. That's why this doesn't start exactly at the origin, but it starts a bit further. This is the extremal point. Which is connected to the small solution, but still has positive specific heat, because you see that the slope here is good, is positive. But yeah, that's why I didn't start it, you don't start with extremal. Yeah, that's why you don't start at the origin.
Okay, thank you.
So, sorry, can you
exactly.
repeat the microphone?
Yeah, the entropy, I erased lots of formulas, but yes, the entropy is pi r plus squared.
Square. So in this situation, R plus does go to 0, and
it does
we
not.
still have an entropy, but the temperature goes to 0, right?
So
at the external limit.
So R plus doesn't go to 0.
Yes.
You have that R plus coincides with R minus, like if you had to do the limit appropriately. So the entropy is pi multiply r plus squared. That does not go to 0.
Okay.
But the surface
temperature?
gravity, you can have it go to 0
Okay.
because the two horizons coincide.
Yes, yes, okay.
That's also another consequence. When the two horizons coincide, in general, the temperature goes to 0.
Okay. But for both cases, we have, for the first graph and the second graph there, we also have the extremal limit behavior, right? Because
Yes.
we have an extremal high noticeable black hole below and over the critical charge.
Yes.
Charge.
Yes, yes.
Okay, but
You can have
only
it.
for the first, second case, it's more interesting.
Yes, only for the second case, you have this particular non-monotonicity of this.
Perfect.
Here, yeah, you still have the extremal, and then it goes all the way monotonically. It doesn't do much.
Thank you.
Hi. When we normally think in statistical mechanics, I have in mind that we are tracing in some Hilbert space. Louder? Okay. The partition function which is the thing that you use in statistical mechanics, is tracing in some Hilbert space. And here you find that there are three sectors to sort of pick.
Yeah, well, three branches, yes.
And you pick I wanted to ask if there's a way to think in how you can understand the dynamics in that Hilbert space between these different contributions.
Yeah, so given the fact that you have these ADS black holes, you should be able, if you had full computational ability, infinite computational ability, you will be able to compute the partition function of the dual field theory, that you can count states and so on, and you should be able to see a behavior of this, like let's say, on going to this direction here. You should be able to see this direction. It's just that computing the partition function of the dual field theory at non-zero temperature is very complicated.
Okay.
So what the dual field theory, what people manage to do in the dual field theory is basically compute the entropy of the Hilbert space, like to retrieve the partition function of the extremal supersymmetric limit. Once you add temperature, we are a bit far, at least for the theories which are dual to this sort of black holes. We were not able to reproduce this thing on the dual field theory, unfortunately, not yet. There have been some studies, but for theories which are three-dimensional theories, but they're not quite the one that are dual to this sort of black holes. They have a different, I can explain a bit more. Like Shiraz Miwala did a lot of computation in this regard, but it's not quite yet that we can reproduce this at the microscopic level, unfortunately.
Anyone else?
Another very naive question. Only in ADS these things happen, only if I consider negative. There is no way if I consider positive cosmological constants, like Kerr black holes with cosmological constants, something like that.
I mean, I don't think that, well, I guess no, because in general, once you have the sitter, you have a cap to your, to the size of your black hole will be capped by the cosmological horizon. So you will not be able to have something like a large black hole in a way. So you will have different, let's say different, I guess that you will still be able to have different branches, but for sure not the same as this one. For sure not the large one. I guess that maybe, another speaker that will come next week, Tarek, also studied phase transitions in the sitter. So maybe it will be, but I'm pretty sure that it would not be the same flavor as this one, but it might be some other kind of phase transition.
Thank you.
All right. Perhaps one more. Yes.
Yeah. Probably I missed it, but what will be the procedure to obtain this critical Q?
It would be basically, so if you start from this one and you lower the charge of your system, eventually you will start from, let's say, I'm gonna write it here, so you'll have something like this, then will start being something like, then you will start seeing an inflection point. So when you start seeing this, I mean, there will be one point in which it will start, like, let's say, it will approximate this one. The point at which it starts having this inflection point, it will be at Q critical.
Okay.
Let's say. So you will have like some sort of discontinuity in the first derivative. Okay. While here you have two minimum and maximum, these two will start coincide, and then you will not have you will not have the curve anymore. That would be exactly at the point in which it would be Q critical, and it will correspond to this one, like this point here.
Okay, thank you.
And these people found that, yeah, in general, it goes like this. Like it is related to the square root of the cosmological, of the minus, I mean, the cosmological one is negative, so depends on how you define it. Maybe here I didn't define it.
Okay, great. Thanks for all the questions. Thanks, Chiara. So let's go to lunch. And we meet at 2:30.
I figured it was like 12:30, and I said, wait a moment, I have to finish. Yeah, maybe. I think it's like I think it's and you know, some exercise you can really plot it with Mathematica, so you can. It's really easy to kind of see it in Mathematica if you want to have it. Yes, yes.
I do have a picture of microstates or just like particles in water, and I can picture, like, for example, a piece in which I have gas and liquid.
Yes, yes. So yes.
But for black holes, beyond the CFT picture, do I have, like, what should I picture, like, some sort of hypothetical microstates of black holes? Some of them will correspond to a small one, and some of them will correspond to a large one.
I think overall, I mean.
Perhaps it's not even a well-posed question. But you know what I mean? In water,
But
I have seen videos of water in this existing.
Yeah, with the bubble, yeah, with like so bubbling, and yes, yes. So, I don't know. I think that in gravity, what you will see only small until here and large until here. Let's see how to. Okay. So I think so. You know, the bubbles that you will see will correspond to either this one or this one.